Hello Math 4411 students. Let's begin lesson 4, cyclic groups. Do you remember cyclic subgroups from the previous week? It goes like this. If there's a group and it has a subgroup of just one generator, then we call it a cyclic subgroup of the original group. Now, consider this case. That subgroup happens to be the same as the original group. That original group is called a cyclic group, and that's the topic for today. Let's begin with a review. First, the exponent rules. Let's begin with a group G, an element A, and an integer n. We define the power expression a to the nth power like this, a repeated application of the group operation, repeated n times, starting from e. So when n is 0, that means no a is applied here, so we stay at e. If n is 1, then applied only once, so e times a, so we have a. N is 2, then applied twice, e times a times a. So we have, well, a squared expression, and so on and so forth, and that's repeated n times. That's a to the n power. That works for n is greater than or equal to 0. Now, what if n is negative? In that case, we do the same thing. We do the repeated application, but we do it with a inverse. That's how we define the power expression a to the nth power. Now, this is good for all groups, abelian or non-abelian, typically non-abelian in general. For abelian groups, I find it a little bit more convenient to use addition notation like this. Either way, it works out for abelian. For non-abelian, of course, you can't do this. You have to do it this way. Now from here, you can easily deduce exponent rules. Rule number 1, rule number 2, and rule number 3 like this. The proofs are left to the students because it's elementary. But tedious, very tedious actually, because we have to consider when m is non-negative and n is non-negative. M is non-negative and n is negative, and so on and so forth, 4 times. And then for each, you have to count appropriately, prove this, and that. Elementary, but tedious. Let's suppose everybody went through that already. And let's say exponent rules are done, and let's review cyclic subgroups. Let's begin with a group G and an element A from there, and the set of all the powers, set of all a to the nth power expression forms a subgroup. It's an abelian subgroup as a matter of fact, and we proved it last week, remember? We call it the cyclic subgroup of G generated by A, and we denote it using the triangular bracket like this. Here, the element A is called a generator of the cyclic subgroup. By the way, this is the cyclic subgroup, and this is a generator, because given A, it can generate only one cyclic subgroup of G, so it's the cyclic subgroup, but the same cyclic subgroup can have multiple generators, so it's a generator. It can have other generators too. It turns out the cyclic subgroup is the smallest subgroup that includes A. That means if there's another subgroup, say H, that includes A, then that subgroup H must contain the cyclic subgroup as well. So the cyclic subgroup is the smallest. Finally, if this cyclic subgroup happens to be the entire group G, if it covers entire original group G, then we call the original group G a cyclic group generated by A. Let's look at some examples, and here's a nice example. Very, very typical example. The set of all integers, that's a cyclic group generated by 1. Elements here look like this, 0 plus 1 plus 1 plus 1 plus repeated many times like this. So add it 0 times, you get 0. no addition at all. Add it once, then 0 plus 1 is 1. Add it twice, 0 plus 1 is 2, and so on and so forth. And then that'll cover all the non-negative integers. And for negative integers, they look like this. They can be covered like this by whatever repetition. So yes, this is a cyclic group. Oh, by the way, if we take negative of negative 1 again, we come back to this. So this argument proves that Z can be generated by not just 1, but can be generated by negative 1 as well. Is there any other generator? Good question. Think about that. The next example, MZ is a cyclic subgroup of Z. So this is a cyclic group too. What is MZ? M times an integer. That is the set of all multiples of M, or set of all integers divisible by M. And the elements here look like this. 0 plus M plus M plus M plus repeated whatever times. And then 0 minus M, minus M, minus M, repeated whatever times. Again, minus of minus M, we come back to this. So we can conclude that this can be generated by not just M, but negative M as well. The same question again. Is there any other generator, or just these two and no more? Think about that. Next, Zm is a cyclic group. Remember this? The residue class? It turns out Zm is a cyclic group as well, generated by 1 bar. By the way, do you remember all those? Let's see, in week 1, we went through the equivalence relation and we defined the residue class Cm as a quotient set of the equivalence relation defined by congruence modulo M. Remember that? That's what we did in week 1. And then in week 2, we came back to this residue class and proved that addition is well defined here, the induced addition, and then that forms a group structure. And then Zm is a finite group of order M. We did that in week 2. Now let's come back to Zm again. This time, let's check whether this is a cyclic group. The answer is yes. Elements here look like this. 0 bar, 1 bar, 2 bar, all the way over to m minus 1 bar. There can't be anything else because of the division algorithm, and we established all that in week 1, remember? And then here, arbitrary element look like this, k bar. And then that is basically k times 1 bar. What do you mean by that? That is, we begin from 0 bar by definition, and then add up 1 bar how many times? Repeatedly? K times. That's what this means, and these, all those means. In general, like this. And now, if k exceed m minus 1, then you go back to 0 again, and then 1, and then wrapping around again. Remember all that? So we have a cyclic group. You can start from 1. Now, is that the only generator? Well, certainly not. You can consider -1 as well. What is -1 bar? -1 bar is actually this one here, m-1 bar, because m is congruent to 0. So this is basically 0 minus 1. And then, are there any more? Well, think about that. Now let's go to the fourth example. Z2 times Z2 is not a cyclic group. What is this? It's a Cartesian product with additions, so it's going to be a vector addition, component by component addition, but there's easier description. Klein's 4 group, or the 4 group, as Klein himself wrote, and the term 4 is 4 in German, and it begins from V, or in German, V. So Klein used V as this notation, so by tradition we use V for this. And then it turns out that this forms a group. Not only that, this is isomorphic to Z2 times Z2 through this kind of construction. So Z2 times Z2, so this is a Cartesian product. Z2 has 2 elements, 0 bar and 1 bar, and then another 0 bar and 1 bar, 2 components, so we have 4 elements like that. And then you can rename it as E, A, B, and C to form this. And the addition is defined component by component, the vector addition, with this rule. 0 plus 0 is of course 0, 0 plus 1 is 1, 1 plus 0 is 0, excuse me, 1 plus 0 is 1, sorry about that. 1 plus 1, and that's 0. 1 plus 1 is 2, but that's equal to 0, or equivalent to 0, modulo 2. And then, if you summarize them all, then you end up with this group operation table. And if you compare this one and that one, they're identical. Just rename this as to E, A, B, C, E, A, B, C, and write those, and you're going to get this. So let's come back to this. And let's prove that this is not a cyclic group. How do you prove that? Well, in order to prove a certain group is a cyclic group, you have to find a generator. A certain generator that generates entire group. You have to prove that this is not a cyclic group. That means there's no generator. There are 4 elements, and check all 4 elements, and then none of them generate entire V. It turns out, well, like that. A does not generate everything. It leaves out B and C. B does not generate everything either. It leaves out A and C, and so on and so forth. And E, of course, does not generate anything except for itself. So that's trivial. Let's look at this. What is this cyclic subgroup? Look at this table. E times A is A, and A times A is E. So times A again, then you're going to get E times A. Times A again, you're going to get E. Times A again, we're going to get A. Times A again, we get E. So we're going to get bouncing back and forth, E and A. So you're going to get all these. So B and C do not belong to this. So A does not generate everything. And you can check the others the same way. Consequence? Klein's 4 group, the 4 group, is not a cyclic group.